Dear children, in today's class, we will be discussing magnetic field due to the circular loop. Then we discussed how magnetic field pattern will be around the solenoid. Then even we discussed how the magnetic field will be around the electromagnet and what are the similarities between solenoid, that is current carrying solenoid, with what we can say bar magnet, and even what are the differences between the electromagnet and permanent magnet. Okay, fine. And before getting to our topic, let us recall what we had discussed in a previous class. Children, in a previous class, we discussed about Oersted experiment, and even then we discussed about right hand thumb rule, and even we discussed about the magnetic field around the current carrying straight conductor. So let us recall what actually Oersted experiment proved actually. So Oersted experiment proved that there would be a magnetic field around the current carrying conductor, which means what? Whenever current passes through a wire, children, that wire might be a straight wire or it might be a circular wire, whatever it may be. If current passes through a conductor, through a wire, through a coil, definitely there would be a magnetic field. There would be a magnetic field. But children, how to prove that there will be a presence of magnetic field near the current carrying wire? Again, I am telling you children, wire means it might be straight, it might be circular wire. But how can we say, how can we prove that there will be a magnetic field near the current carrying conductor? So obviously we are going to use magnetic needle. So with the help of magnetic needle, dear children, we will come to know that there will be a presence of magnetic field near, that is around the current carrying conductor. But how this north pole of the magnetic needle gets deflected when current passes through a conductor? Children, examination point of view, it's very important actually. So here actually we have four cases. We have four cases with Oersted experiment. So the very important thing is that whether current carrying, what we can say, wire is placed above the magnetic needle or below the magnetic needle. This is very important. Children, once again let us see here. In first case actually what we have done, it is north, east, and here is the west. So children, according to the Oersted experiment here, what happens here? See, children, it's very important. Children, here first case is a case, second case. So in the first case, what are we doing here? Current carrying wire is placed above the needle. Children, it's very important. So needle will be here. Above this current carrying conductor is placed. It's very important. Such a way that how the current is flowing. So in this direction. I mean what? South to north. So when a current carrying conductor is placed above the magnetic needle, such a way that current flows from south to north, then the north pole of the magnetic needle gets deflected towards west. Very important. Means when current flows from south to north, then north pole of the magnetic needle gets deflected towards west. Whereas when we reverse the direction of current, I mean what? If you reverse the direction of current, which means what? When current flows from north to south, then this north pole of the magnetic needle gets deflected towards east. But children, these are the cases where current carrying wire is placed above the needle. Now come to this one, second case here. Here current carrying wire is placed below the needle, children. Means magnetic compass is placed now above the current carrying wire and the current carrying wire is below the magnetic needle. Then look at here what happens. If current is flowing from south to north, in this direction it is going, that is south to north. That is when current passes from south to north, then north pole of the magnetic needle, this is the opposite to these two cases, children. It's very simple. If you are working with these first two cases, the second two cases are quite opposite. So if current passes from south to north, then north pole of the magnetic needle gets deflected towards east. Again, similarly, what happens when we reverse the direction of current, magnetic needle also reversed, magnetic field also reversed. How can you say that magnetic field also reversed? Because north pole is deflected now in opposite direction. That is, when current flows from north to south, it gets deflected towards west. So children, this is how actually we have to say about the deflection of north pole. When it is placed above the needle and it is placed below the needle. So these are the actually conclusions of ICSE experiment. But in children, or with the help of ICSE experiment, you know, it's very clear that there will be a magnetic field around the current carrying wire. But we cannot say in what direction that field is. For that actually we have right hand thumb rule. We discussed about actually right hand thumb rule. Right hand thumb rule. Children, this rule is very, very important in order to understand the magnetic field around the circular loop. So without this we can't understand this. So let us recall this also. Right hand thumb rule. So what is right hand thumb rule? Children, let us say here is current carrying conductor through which current is passing like this. Okay. Let us take the two wires. Let us take. What is the difference? Children, you have to imagine, again I am telling you, this is a wire in which current is passing vertically upwards. This is a wire in which current is passing vertically downwards, like this. First case, current is passing vertically upwards. Then according to right hand thumb rule, this current carrying wire should be held with right hand such that thumb shows the direction of current, then these four fingers will give you the direction which we are curling, we are closing, will give the direction of magnetic field. Now children, in this, according to this right hand thumb rule, now you tell magnetic field lines around the current carrying wire, in this case and in this case. Now you tell me in which case the magnetic field lines are clockwise direction, in which case they are anti-clockwise direction. Children, think, come on. Here we have two cases. Case 1, case 2. In the first case, current is passing vertically upwards and here current is passing vertically downwards. So in which case magnetic field lines are clockwise direction around the conductor, and in which case magnetic field lines are anti-clockwise direction. Children, come on, think. When you can understand this concept clearly, then only you can understand this magnetic field of the circular loop, even solenoid, even about electromagnet. So this is a basic point in order to understand the next very important application topics. So very application oriented topics, very important. Come on children. So here what is happening here? Current is flowing vertically upwards. So let us assume, okay, it is current carrying wire. In this, how the current is flowing? Vertically upwards. So what I have to do now? Come on. I have to hold this right hand, current carrying wire with the right hand, and my thumb must be in which direction, dear children? Current direction, that is vertical upwards. Then look at here, fingers. Now, is it clockwise or anti-clockwise? How to understand? Just you have to observe from the top. Like this, children. So just you have to observe like this. So here you are holding current carrying wire with the right hand. Yes, thumb is showing that is vertical upwards, current direction, and these four fingers, or in which direction we are curling? We are curling in anti-clockwise direction. The simple one I will tell you. If current is coming towards you like this, I am curling. So in which direction? These four fingers are closed, anti-clockwise direction. So here anti-clockwise direction. Anti-clockwise means this is like this. So obviously when you reverse the direction of current, that is when current is vertically downwards, in which direction we are curling, in which direction we are closing these four fingers? Clockwise direction. So that is clockwise direction. That's it, children, over. So this is what actually right hand thumb rule. Now same concept we are going to use to understand the magnetic field around the circular loop. Okay children, so again I am telling you this is very important. The simple way you can remember that when current is passing vertically upwards perpendicular to the plane of the paper, the magnetic field will be anti-clockwise direction. Whereas if current is passing vertically downwards to the plane of the paper, then the magnetic field will be clockwise direction. That's it. Okay, fine. Now children, look at here. So this is a magnetic field, and here is a, we are going to discuss the magnetic field around the circular loop. So how this circular loop is formed? Children, let us think it is a cardboard. Here is a cardboard. Just you think that it is a cardboard. Okay. And here two holes are made. Two holes are made. And I have very long copper wire. Okay. That end of the copper wire, just I place through first hole. Okay, and I will get like this. Okay. Again this end is passed through here. Again from here it is taken. So like this we can make a one circular coil we can make. Okay. So this is how actually it appears. And the two ends will be there, right? The two ends, finally after making a coil, the two ends will be there. The two ends are connected to the battery, key, and here is the rheostat. Children, what is the purpose of rheostat? To change the amount of current. I mean, we can increase the current, we can decrease the current. Now children, let us switch on this. Yes, the switch is on. Then what happens? It's very, very important. Whenever you are discussing about loop, the current direction is very important. So if you want to know the current direction, you must see the terminals of the cell. So here is a positive terminal, here is a negative terminal. Now what will happen? Current direction will be like this. Current is passing like this. So let me highlight with the, fine. So this is current direction, children. So here current direction will be like this, upwards, and here is current direction will be like this, and here is current direction will be like this. So this is the current direction. Fine. Means here now, children, try to understand. We are facing the coil. Try to understand. We are facing the coil. First, how the current is appearing, children? Current is appearing clockwise direction. Children, I said that these terminals are very, very important, because when we reverse the terminals of the battery, then what will happen? Current direction will be reversed. That time it will become anti-clockwise direction. So it should be very, very careful. We must be very, very careful. So whenever we are starting, when we start to think about the magnetic field around the circular loop, first we must concentrate on the terminals of the cell. Terminals of the cell only. Okay, fine. So as is positive and negative, and we know that current always flows from positive terminal to negative terminal. Now children, how to understand how the magnetic field is going to be? So let us say this point where this one end is there. It's not an end in between actually. It's not an end. It is near the hole. There is the point is P and this point is Q. Now children, for a while, you forget that this is a circular coil. Just you forget the circular coil. From here to here, just can we consider what we can say conductor? Of course we can. So any part of a loop is a conductor only. Any part of a loop is a conductor only. So from here to here, we can assume as a conductor. From here to here also we can assume as a conductor. So this part of P, this is a P, it's a conductor. Here is a Q, is a conductor. Now the thing is that, children, at a point P, how the current is flowing. At a point Q, how the current is flowing. Children, don't you think that at a point P, current is flowing vertical upwards? Children, just imagine. Means here, it is like this actually. Okay, now. And this is a point here, current is flowing like this, vertical upwards. Okay, whereas at a point Q, current is flowing vertically downwards. Try to understand. Here at a point P, current is flowing vertical upwards. At a point Q, current is flowing vertically downwards. Okay, fine. Now, we know that whenever current passes through a conductor, there will be a magnetic field. But how the magnetic field pattern, how to identify, how to know actually. But children, generally, so actually it is an activity. Generally, try to understand, very, very important thing is that we cannot see the magnetic field, that we know very well. It is invisible. Then to have that vision, what we'll do, we'll take iron filings, we'll try to just put on this. Okay, then what will happen? We'll try to tap it. Okay, means when the current is flowing in this coil, we'll try to just slowly tap it, so that we will notice that what we can say iron filings, children, they'll get adjusted near point P, near point Q. How they'll get adjusted? They'll get adjusted as a concentric circuits. Very, very important. Children, before starting this experiment only, on this cardboard, we will sprinkle some iron filings. The moment when you turn on the switch and just try to tap it, and we will notice that iron filings will get adjusted as concentric circuits. How? Let me tell you like this. So this is how they'll get adjusted. So this is how actually children the iron filings will get adjusted as a concentric circuits around this point and around this point actually. And children, here the very important thing is that then how the magnetic field direction at a point P, at a point Q, and if you can notice whole circular loop, how the magnetic field will be. So for that only we are going to use again right hand thumb rule. Look at here. Don't you think it is like a point P? It is a point Q. Obviously. So it is like a point P only. Okay, point means at a point P, magnetic field, at a point P, current is flowing vertically upwards. At a point Q, current is flowing vertically downwards. So at a point P, as the current is flowing vertically upward, children, how the magnetic field will be? The magnetic field pattern will be anti-clockwise direction. That is, here the magnetic field pattern will be like this, children. So this is how magnetic field lines anti-clockwise. So these are all going to be this spiral. So anti-clockwise direction. What about Q, children? At a point Q, current is flowing vertically downwards. So whenever current flows vertically downwards, how the magnetic field will be? Magnetic field will be clockwise direction. Magnetic field will be clockwise direction. So this is how actually. So children, the magnetic field due to the circular loop appears like this. It looks like this. Children, this first you have to think individually. At a point P, how the magnetic field will be? At a point P, magnetic field will be anti-clockwise direction. Where at a point Q, how the magnetic field will be? At a point Q, the magnetic field will be clockwise direction. Look at here. At a point P, as a current is flowing vertically upwards, children, the magnetic field will be anti-clockwise direction. The magnetic field will be anti-clockwise direction. Whereas at a point Q, current is flowing vertically downwards. Then according to right hand thumb rule, the magnetic field will be clockwise direction. Clockwise direction. But children, at the center of the coil, at the center of the loop, try to understand. It's very important. Children, at the just you notice, try to notice here at the center. Of course, here anti-clockwise, here clockwise. What about at the center of the coil, children? At the center of the coil, don't you think that all magnetic field lines are in the same direction? Yes. All field lines, very important. Field lines are in the same direction. In the same direction. And children, you can notice there will be a uniform magnetic field. Means here all magnetic field lines are in the same direction. The space between the magnetic field lines also same only. Very important, children. At a point P, the magnetic field pattern will be anti-clockwise direction. At a point Q, magnetic field line pattern will be clockwise direction. But whereas at the center of the coil, children, the magnetic field lines are in the same direction. So there will be at the center of the coil, there will be a uniform magnetic field. And children, the very important thing is that here, now children, in this case, as the current is flowing clockwise direction, but how the magnetic field lines are entering? Children, don't you think that they are entering into the coil? Children, they are entering into the coil. Means what? On whole, there will be a magnetic field around the circular loop. But children, if there is a magnetic field around the circular loop, definitely there should be a north pole and there should be a south pole. There should be some polarity. But how to identify the polarity? Which phase of the current carrying circular loop or circular coil behaves like a north pole and which phase behaves like a south pole? Children, examination point of view, this is very important. In exam, the simple diagram will be given. They will ask us to identify whether the phase which we are facing, okay now, the side which we are facing, will it be south pole or north pole? So how to identify? So that we will discuss now. Children, examination point of view, identifying the south and north polarity is a very important. Children, to understand that, first small point we have to recall. Children, here is a bar magnet, here is a north pole and here is a south pole. Children, in external magnetic field, at what end the magnetic field lines will leave, at what end magnetic field lines will enter, children? We all know very well that at a north pole, magnetic field lines will leave, okay now. At a south pole, magnetic field lines will enter, like this. Or in a simple way, let us see, all will leave at a north pole, whereas all will enter the south pole. Children, try to answer, very important. Means, children, again I am telling you, the end through which field lines are entering is going to be a south pole. The end through which field lines are leaving is going to be a north pole. Now children, let us assume this as a coil. Children, try to understand. Circular coil. Children, here imagination is needed. Children. Then only we can understand very easily. Children, and again telling you, this part of the topic is very important to understand the solenoid, to understand the electromagnet. Okay, fine. And examination point of view also, this is a point where they are asking the questions regularly. Okay, now this is circular coil. Okay, now this is the circular coil. Children, here two faces are there. This is one face which is towards you, and back side one more face is there towards board. Right to understand. There are two faces of the coil. One face is which is towards you. One more face is towards coil. Board. Now children, for you, the current is flowing in a clockwise direction. Right to understand. Like this. Current is flowing like a, for you, current is flowing in clockwise direction. Children, then for me, current is anti-clockwise. Try to understand. For you it is a clockwise, but for me it is anti-clockwise. Fine. And how the magnetic field lines, they are entering like this, children. Zing, zip, like this. Zing, zip, like this they are entering. Means they are entering. Let us say this is the first phase. Let us say the second phase. The side which is towards you is the first phase. The side which is towards me is the second phase. But how the field lines are entering, children? The field lines are entering like this. Zing, zip, like this. They are entering like zing, zip. I mean what? This is a phase through which field lines are entering. Then children, now look at these two ends. Where the field lines are entering? At a north pole or south pole? Hey, it is south pole only. So at the south pole only, field lines are entering. So here, this side field lines are entering, which means what? This side is going to be a south pole. And as they are entering here means, yes, they have to leave from this side. So from your side, field lines are entering. From my side, field lines are leaving. So children, this side is going to behave like a south pole and this side is going to behave like a north pole. So simple. As simple as that. Very simple, children. Now look at here. So in exam, how they'll ask you, you have to think only one side, children, because one side if you can identify, other side will be opposite, obviously. If one side is south, another side is going to be obviously north pole only. Children, in this case, look at here. So current is flowing in a clockwise direction. And here, field lines are entering. So this face of the coil, the face which is towards you, is going to behave like a south pole. And other side will be there, other side, that is going to be a north pole. So children, this only means this can be well understood with the help of actually clock rule. This one we can call the clock rule. What is a clock rule, children? Children, they may ask us in exam, state the rule which is used to identify the polarity of the current carrying circular loop. And what is that rule, they are asking. Children, here is a clock rule which we are going to use. Very simple actually. So what is that clock rule, children? So here we are facing the coil. It's very important. We are facing the coil such that if current is flowing in a clockwise direction, then that phase takes south pole, or if we are facing a coil, so that if current is flowing in an anti-clockwise direction, then that phase takes a north pole. So very simple. Children, to understand this, we have one more simple trick. Very easy. So in examination, we don't see all these things. Simply we will see whether current is flowing in a coil clockwise or anti-clockwise. Because on paper the diagram is given, obviously we will be facing. So we don't think whether we are facing or not. Because on paper 2D diagram, obviously we will be facing that only. So children, look at here. I'm including children. This is a clockwise. Here is a coil in which current is passing clockwise direction. Current is flowing. Here current is anti-clockwise direction. Now look at here. Like this. Now look at here. Children, here. Look at here. Okay. This is also okay. Now look at here. Fine. Over. Now, can you feel any letters? Obviously, here S. S represents south. South. N represents north. Over. That's it. Means how the current is flowing, children? Clockwise direction. So we are facing the coil. So if current is a clockwise direction, that face takes south polarity. Whereas if we are facing the coil, children, so the current is flowing in anti-clockwise direction. Then that face takes a north polarity. That's it. So children, this is about magnetic field around the circular loop or coil. So examination point of view, this is very important. This is very important. Means your concentration should be here, terminals only, because when we can change the terminals. Children, now look at here how the current is flowing clockwise. So clockwise, so south pole. If you change the terminals, then what will happen? Current will be anti-clockwise direction. So that takes is the north polarity. Children, okay children, just copy the diagram. Just better you copy this. Then we will start solenoid. That is current carrying solenoid. Okay, copy it. So this is how actually solenoid seems to be, plus minus. So children, now we will see how the magnetic field will be around the current carrying solenoid. So first of all, children, what is a solenoid? Children, solenoid means don't think that it's something which is like complicated. It's not. It's very simple. You know, in some pens, you know, spring will be there. Spring. How it will be? Helical shape. Yes. Simply it is. If it is made up of with a copper coil through which current is passing, then that spring we can call it as a solenoid. Solenoid is what actually? Scientific name. That's it. The spring must be made up of with a copper coil, copper material, and through which current should pass. That we can call it solenoid. So look at here how the definition will be. So if a conducting wire, so just you take a long conducting wire and that is wound. So if a conducting wire is wound in form of a cylindrical coil, like a spring. Cylindrical coil in the sense spring. Children, spring shape, you know? Yes, spring. Okay, no? And such a that its diameter is less in comparison to its length. So it is, look at here. This is a wire taken and it is wound in form of a cylindrical coil. So, such a that its diameter should be less comparatively its length. Means length should be more and diameter should be less. And through this if current is passing, then this only we can call it as a solenoid. So the thing is that actually how this current carrying solenoid is going to behave. It's very important. And what are the similarities between solenoid and bar magnet, and what are the differences also? Means how solenoid is better over a what we can say bar magnet. Children, these 2 points are very important examination point of view. Children, first got this vision or not? This just imagine that. Let me show you this. Children, look at here spiral binding nodes. Forget about this complete nodes. So this complete nodes, no, just leave the complete nodes. Only concentrate on this spiral. So concentrate on this spiral. Children, this is very so if this spiral, if this one is, now it is a plastic actually. So if it is made up of with copper wire, and 2 ends will be there, you know, here is, let me show you one end. Yes, can you see one end? Yes, here one end will be there, here one end will be there, and this side also one end will be there, this side also one more end will be there. So these 2 ends are connected to this battery. Then this only we are going to call it as a solenoid. Okay children, fine. And we know that means already we discussed the oil side experiment, current carrying straight wire, loop we discussed. Children, don't you think that this solenoid is nothing but the combination of the loops only? Obviously, Each and every one is a loop. Loop. It's a combination of loop. Means each and every, whenever current passes through a loop, children, it behaves like a magnet. Now it is a combination of loops. Obviously, this entire setup also going to behave like a magnet only. So it's very important. Means the current carrying solenoid is going to create a magnetic field around it. But how the magnetic field pattern will be? How it is similar to the bar magnet? Then let us recall about a bar magnet. Children, let us look at here. It is a bar magnet. It's bar magnet's north pole and the south pole. Children, how the magnetic field will be around the bar magnet, children? Field lines will move like this. Ching, ting, ting, like this. So this is a beautiful magnetic field around what is, it's a north pole. So field lines will be coming out of the north pole, will be entering into the south pole like this actually. So it is also noticed that if current is passing like this, children, if near to this, if iron filings are sprinkled, then they will get adjusted as like this only. Means what? The magnetic field around the current carrying solenoid resembles the magnetic field due to the bar magnet. Which means what here? The magnetic field around the current carrying solenoid and the magnetic field around the bar magnet are same to same. Both are similar. So children, as we are saying that current carrying solenoid also means around this also magnetic field will be there. So as magnetic field will be there, children, so there should be south pole, there should be north pole. How to identify the south pole and the north pole of the solenoid? Children, this is very important. So here only we need the concept of the clock rule again. We need the concept of clock rule. Children, first let us identify the direction of current. So here is when we switch on this. Okay. So current is passing like this. This is current is entering here and here is current leaving. And children, don't come to the conclusion by saying that here this is clockwise direction, though this phase. No, it is wrong. That you cannot see this one, children. No. At the end, how the current is entering and another end, how the current is leaving is very important. Children, for suppose, just children, it's very important. Here you need imagination like anything. So let us say it is a coil, children. This is a coil. Now this terminal is connected to the positive. This terminal is connected to the positive terminal. Then what will happen here? This is connected to the positive terminal, means this end is connected to the positive terminal, and this end is connected to the obviously negative terminal only. And here, children, I'm going to put, wait, let me take this one. Yeah, fine. Let me make more this one. Yes. Fine. So children, this is the end where it is connected to the positive terminal. So current will be entering. Children, now you tell me how the current is entering for you. Come on, children. So current is entering like this. Ting, ting, like this. So current is entering like this. Children, current is entering like this. Is it clockwise direction or anti-clockwise direction? Current is entering in an anti-clockwise direction. Children, whenever we are facing the coil, if current is entering in a anti-clockwise direction, then that phase behaves like a north pole. That phase behaves like a north pole. Obviously, children, here current is entering anti-clockwise direction. Now let me explain about this end. Children, I am changing this one. Yeah. Now this is the end where current is leaving. Children, look at here. How the current can leave? So this is current will coming like this. Current is leaving. Children, look at here. How the current is leaving? Current is leaving in a clockwise manner. So it takes south pole over. So children, you have to notice, you have to understand how the current is entering at the ends, how the current is leaving at the ends only, not like this. It is a clockwise direction, it is anti-unhole. No, that is wrong here. At the ends we have to. And children, so as it is behaving, it is like a north pole. Children, again I am telling you, here current is entering anti-clockwise direction. Here current is leaving clockwise direction. It is not my wish, it is not your wish. So based on the clock rule only, we will decide. Now then, how the magnetic field pattern will be? Obviously, north pole to south pole like this. So it is noticed that field will be like this, north to south. It is noticed like this, children. So let me draw like this. So this is how magnetic field pattern around the current carrying solenoid. Look at here, same to same. So what is the similarity? First similarity, children. First similarity. The magnetic field around the current carrying solenoid will be same as it of the magnetic field around the bar magnet. That is the first similarity. And what is the second similarity? Children, in a previous classes, I mean in a 9th class or 8th class, you have studied the properties of the magnet. What happens when a magnet is suspended freely, children? When a bar magnet is suspended freely, what will happen? It will come to the rest by showing geographical north and south. Now children, similarly, when current carrying solenoid is suspended freely, also what happens? It will come to the rest by showing geographical north and south. Hence, we can conclude that current carrying solenoid behaves like a bar magnet. So children, in exam they may ask you to write the similar. First question they will ask you, how does a current carrying solenoid behaves? So you should write it behaves like a bar magnet. Then they will ask you the questions. What are the two similarities between the bar magnet and current carrying solenoid? Two similarities, children. So magnetic field will be same. First point. Second point, when current carrying solenoid is suspended freely, it will come to the rest by showing geographical north and south. So these are the similarities. That is fine. Then what are the differences, children? Then what are the differences between solenoid and a bar magnet? Also very important examination point of view. Children, first one. Here, children, it is a north pole and south pole. Can we change the polarity? Can you change the polarity? Hey, don't say that, sir, I will put like this so that I will change. No, not like that. It's cheating. So it's not like simply, sir, if I turn magnet like this so that it will become south, it will become north. Not like that. A given polarity, a given north pole, it is a fixed, the magnet is fixed like this only. Can we change this north pole, this south pole by doing something? No, we can't change. So children, in the case of bar magnet, polarity can't be changed. But whereas children, in the case of solenoid, the polarity depends on the direction of current, and the direction of current depends on the battery. Children, in this case, this side is behaving like a north, this end is behaving like a south. What if I change like this? This is negative terminal, it is a positive terminal, the minus is placed. If I do like this, current direction will be reversed. Then this side behaves like a south, this side behaves like a north. So, in the case of bar magnet, children, polarity can't be changed. But whereas, in the case of solenoid, polarity can be reversed. How? By reversing the direction of current. Children, note down, it's very, very important. In the case of solenoid, polarity can be reversed by reversing the direction of current. That's the first difference. And second difference, children, see, here magnetic field strength is measured in terms of Tesla. So this will be discussing in the next class actually, Tesla. For example, for this given bar magnet, the magnetic field strength, let us say, is 30 Tesla. Means can we increase this 30 Tesla? We cannot increase. But can we decrease? Of course, children, we can decrease the strength of any magnet. So for this bar magnet, by tapping, by heating, we can. I'm not talking about decreasing. No. I'm talking about increasing. Can we increase the strength of the bar magnet, children? We cannot increase the strength of the bar magnet. But whereas, can we increase the strength of the magnetic field on the solenoid, children? Yes, we can. There are three ways are there, children. In examination part, it's very, very, very important. What are the ways in which we can increase the strength of the magnetic field around the solenoid? Children, there are three ways. What is the first one, children? Note down, very, 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 very important. So, magnetic field strength of the solenoid can be increased in three ways. The first way, by increasing, so three ways. First one is by increasing current in the coil. But how can we increase the current? Children, here we have rheostat. With the help of rheostat, we can control the current, right? So by increasing the current in the solenoid, we can increase the magnetic field strength. First one. Second one, children, by increasing the number of turns of the coil. For example, now the turns are 1, 2, 3, 4, 5, 6 only, let us say. If you can make it 10 for the same amount of current, in the place of 6 turns, if you can make a 10 turns, the magnetic field strength will become more. I mean what, dear children? By increasing the number of turns of the coil, also we can increase the magnetic field strength. And third one, children, it is a special one, By inserting soft iron core. Are you able to see? Let me check. Okay. Yes, fine. So, by inserting soft iron core means what, children? Look at here. For example, children, it is a solenoid. So, let us say it is soft iron core. So, inserting like this. Not this first one, you can insert big one also. Then what will happen? Children, there is a specialty for a soft iron core. When a soft iron is placed in presence of a magnetic field, it behaves like a magnet and it also produces magnetic field. Children, already this solenoid is producing the magnetic field, and this inside whatever is placed solenoid, what we get or soft iron, also producing magnetic field. So these two magnetic field, the magnetic field due to solenoid and the magnetic field due to this soft iron, both will be added up, and hence what will happen? The external magnetic field will become more stronger. So children, so these are the ways how we can increase the strength of the magnetic field around the solenoid. Children, examination point of view, diagram will be given. They will identify which one is the south pole, which one is the north pole. And the second question, they will ask us to write the differences between current carrying solenoid and first similarities between bar magnet. Then they will ask what we can say differences. Children, two differences. What are those? For a bar magnet, polarity can't be changed, but solenoid polarities can be changed. For a bar magnet, strength can't be increased, strength is magnetic field strength. But whereas solenoid strength can be increased. Here strength can't be increased. Here strength can be increased. What are the ways? So there are three ways by which we can increase the strength of the magnetic field around the solenoid. So this is solenoid versus bar magnet. Now we will see, children, bar magnet, the permanent magnet versus electromagnet. So plus, minus, and here is the rheostat. So children, now look at here. So what actually electromagnet is? Children, by seeing this only, some students will get doubt actually. Sir, what is the difference between solenoid and a electromagnet? So first let us see the difference in a structure, children. In the case of solenoid, it is just a cylindrical copper coil. If you want to increase the strength of the solenoid, you will insert a soft iron core. Am I right? If you want, that is optional but not mandatory. But here, children, this is soft iron core. It is a soft iron. It is mandatory, means on this soft iron the copper wire is wound. Try to understand. In the case of solenoid, this is not mandatory, but whereas in an electromagnet, on this soft iron only the wire is wound. Hope I am clear. So this is a difference. Otherwise, we will get confused. Both are same white color. It's not that. So here is difference is there. Now come back, children. So what is an electromagnet, children? So look at here. So it is a temporary, children. First, why we are saying it as a temporary, children? The thing is that here, as long as the current passes only, it behaves like a magnet. The moment when you switch off the current, then it behaves like a normal copper coil. So that's what we are calling it as a temporary magnet. But children, it might be temporary but very strong. Okay. So it is a temporary strong magnet made by passing current in a coil wound around a piece of iron. This is what it is actually. It is a soft iron. It is actually soft iron. Piece of soft iron actually. Okay. So it is a temporary strong magnet, and here as long as the current passes through it, only it behaves like a magnet. That's what we are calling it as a temporary magnet actually. So children, here of course this actually is I-shaped electromagnet. If you want, you can make a even U-shaped electromagnet. Children, structure depends. But children, so as I said that it is an electromagnet, means it behaves like a strong magnet, means there should be a polarity, right? So which side will act like a south pole, which side will act like a north pole? Children, again same concept of clock rule. By using clock rule only, we are going to identify which side is a north pole, which side is south pole. Children, I think compare with that solenoid diagram, this electromagnetic diagram is very easy to understand. Which side current is entering clockwise direction, which side current is entering in anti-clockwise direction. So examination point of view, again I am telling you, diagram will be given like this. They will ask us to identify which one is the south pole, which one is the north pole. Children, now let us switch on this. Okay, switch on. So plus and minus, so current will enter like this. So current will leave like this, no problem here. But at the ends, how the current direction is very important to us. So children here, so current will be like this, right? Yes. Let me, with red color means it will be high. So this is how actually current will be in each and every turn, and your current will be leaving like this. Children, whenever means to identify the north and south pole, first we have to identify whether current is flowing clockwise or anti-clockwise. For the children, please don't observe like this. No, from this end you have to say, from this end, either this end, children, either this end you have to notice or this end. Then only you can understand. Now, if I am noticing in this direction, so it is, let us say, it is this coil. How the current is? Okay, current is coming like this for me. Current is coming like this. At this end, current is like this. Like this, in this direction is coming. So it is a clockwise direction here. Here clockwise direction. Children, at one end it is a clockwise, means other end you don't need to think. Obviously it is anti-clockwise only. So children, here it is clockwise direction. It is clockwise direction. So here current is leaving anti-clockwise direction. Current is leaving anti-clockwise direction. Children, so whenever we are facing the coil and the current is a clockwise direction, that phase takes south polarity. So this is south and this is going to be north, obviously. That's it. This is going to be north. So this is how actually we can identify the polarity of the electromagnet. Polarity of the electromagnet. Children, here the very important thing is that the differences between permanent magnet and electromagnets are very important. So means previously we have seen the difference between bar magnet, of course, permanent magnet only, between solenoid. Now we are going to see the difference between permanent magnet and electromagnet. So children, let us say permanent magnet here, magnet. So the very important thing is that here, the first point what we can permanent magnets are made up of the steel. Children, permanent magnets are made up of the steel, but whereas electromagnets are made up of the soft iron. Soft iron, made up of the soft iron. And children, here the very important thing is that here polarity can't be changed. Polarity we cannot change. Polarity we cannot change. But whereas here, children, polarity, yes, can be changed. Children, how can we change the polarity? Simple, by reversing the direction of current. Okay, fine. And third one is, children, so here strength of the magnetic field, the strength of the field around the permanent magnet can't be increased. But whereas here the strength can be increased. The strength can be increased. Children, here two ways we have. There are two ways to increase the strength of the electromagnet. Children, examination point is a very important question. In exam, they'll ask us to write what are the ways in which we can increase the strength of the electromagnet. There are two ways. The first one is by increasing the current. By increasing current with the help of rheostat, we increase the current. And the second one is by increasing the number of turns, children. Children, these two are similar to the solenoid. Don't get confused. So this how we have to logically remember. These two are the same. Means in for example, for a solenoid, third one will be there. What is that? By inserting the soft iron core. But here soft iron is already there, so no need to insert. So in the case of solenoid and in the case of electromagnet, these are two common points by which we can increase the strength of the magnetic field. Okay, children, fine. And here, the magnetic field, that is capital B, is a permanent. But here electromagnet, whenever you want, you can switch off the electromagnet. We can take out the magnetic field. How? By switching off the current. That's it. Okay, children. So this is what actually electromagnet and how to identify the polarity of the electromagnet and what are the difference between permanent magnet and electromagnet. And children, applications also very important. Applications where we can use the electromagnets. Where we can use electromagnets. Children, electromagnets are used in various ways actually. So one of the important thing is that electromagnets are used in the cranes, electric cranes, children, in order to lift the heavy iron blocks. Heavy iron blocks, electromagnets are used in the electric cranes. Not only that, children, these electromagnets are used in the electric belts. Children, in exam, they don't ask you to draw the electric bell diagram. They don't ask you to explain about the working of the what is electric bell. But there is even chance of asking one question. So application. So means what is the question we can expect based on electric bell means in electric bell day, children, we use actually soft iron core. So why do we use soft iron core only? Why not steel? Children, why can't we use the steel? Because steel is permanent. Steel is used to make a permanent magnets actually. But here soft iron. Why we use soft iron? Because soft iron, so as long as the current is passing through it, it behaves like a magnet. The moment when you can stop the current, it behaves like a normal soft iron only. That is the reason actually why this soft iron means the magnetic field is induced very easily. It is induced very easily, at the same time stopped very easily. We can produce a magnetic field easily and we can stop the magnetic field very easily. So that is the reason why soft iron is used in the what we can say as a core in the electric bell. Okay children, fine. So these are the topics, children. So again I am telling you, so there is a link between each and every topic. First oil stud experiment, then you should study about the thumb rule, then you should study about the magnetic field around the straight conductor, then magnetic field around the current carrying coil, that is a loop, then you should study about the solenoid, then you should study about actually electromagnet. Okay children, fine. In the next class we will be discussing what happens when current carrying coil or current carrying conductor is placed in a magnetic field. What is going to happen, what is the result, and how can we conclude, how can we make a conclusions, how can we draw the conclusions when we can place a current carrying either conductor or a coil in a magnetic field. Okay children, thank you so much, all the very best.